Welcome to Lesson 7.2, Ratios in Similar Polygons. The learning targets for this lesson are that you should be able to identify and name similar polygons, and that you should be able to apply properties of similar polygons to solve problems. In the next few lessons, we'll actually look at some theorems that help us to prove that polygons are similar, and once again, use the fact that they're similar to solve problems. First off, we'll begin with the definition of similar. Similar is to be resembling without being identical. To resemble without being identical. But similar polygons have something more specific about them, like these two shapes here do, to make them similar without being, and let's say, congruent. They're not congruent because they're not the same shape and same size. But they are the same shape, and they have some things about their angles and sides that make them similar. Similar polygons are polygons whose corresponding angles, by the way, when we say corresponding, we don't mean like the corresponding angles that make the letter F with two lines that are intersected by a transversal. We mean the ones that match up, like an image and a pre-image. Although in this case, we don't see an image and a pre-image. We have them named with different letters. So polygons whose corresponding angles are congruent and corresponding sides. The corresponding sides are not congruent. You can clearly see this from a picture. But corresponding sides are proportional. What do I mean by proportional? I mean that the ratios of the side lengths are the same, or the ratios are equal, making it a proportion. So for this particular case, they have, whenever we write a similarity statement of addition, we actually have to match up the ones that, the angles and sides that match up. So angle A matches to angle E, angle B matches to F, C to G, and D to H. And we can see D and H match up, they're both a right angle. Similarly, the side lengths have to match up. AB must match up to EF, AD must match up to EH, BC must match to FG, and CD must match to GH. And you can see CD and GH match in terms of the angles that touching them being the second marked congruent and the right angle, the second congruent mark and the right angle. Now, when we're checking or verifying that things are similar polygons, we actually would go through and say which parts are congruent. That angle A is congruent to angle E, B to F, C to G, D to H, like a little checklist to show all of the angles, all of the corresponding angles are congruent. And we'd have a similar checklist checking the ratios of sides, checking that 8 over 4, which is 2, is indeed the same ratio as 10 over 5, 12 over 6, and 10.8 over 5.4. So we'd have a checklist there of showing all 4 ratios for quadrilaterals were the same. Describing similar polygons. Given the similar triangles, identify the pairs of congruent angles and the corresponding sides. So they're telling us that these are similar triangles, and we're just supposed to match them up. Given them, identify the pairs. Well, these are both 63 degrees. So angle R is congruent to angle P. I don't know why I did right to left, but I'm doing right to left. That's fine. Angle Q is congruent to angle N. And even though I don't know this, or we do know this actually, in middle school you learned about the sum of the angles in a triangle. We've talked about it a couple times. There is a theorem called the triangle sum theorem. It's in your flipper from Unit 2. But we didn't cover it directly because in Calc Path Geo it's not supposed to be covered till later. But apparently they assume that you already know it. So 180 minus 90 minus 63, since these have to add up to 180, makes both angles M and T 27 degrees. There's also a theorem that we will be proving later that says if two angles are already congruent in triangles, then the third ones have to be also. That's called third angles theorem. But we haven't covered any of that yet, so I just did some of the math. We now have angle T is congruent to angle M. So we now have a triangle, so we have three angles, and we've just shown three sets of congruent angles. So we're supposed to have all congruent angles. And also, by definition of similar polygons, we're supposed to have proportional sides, or ratios that are the same. So in this case, I'm going to do the short over long first. I have 0.5 over 1. So I have QR, I guess I should have done this other way, over NP, which is 1/2 over 1, which, if I multiply by the reciprocal, is just 1/2. Next, I'll do the middle length, QT. QT matches up to MN. They aren't congruent. When I put 1 over 2, I once again get a ratio of 1/2. And I also have the hypotenuse, RT, and in this case the hypotenuse is PM, matching up from the angles that match up, RT and PM. RT over PM is 1.1 over 2.2, which again reduces to a ratio of 1/2. So we have shown, hey, these are our ratios. Our ratios are proportional. They all have the same value, the same ratio, or the lengths of the sides do, and all the angle sets, all the corresponding angle sets are congruent. We're also going to be asked to write what's called a similarity statement. It's a little bit different than our scale factor. It's related though, so we're going to make a note about how it's related right in just a second. So here's what we need to make a note of. Oh, it's going to zoom out. No, we're good. Let's zoom you back in with my little notes. All right, similarity ratio is the scale factor. But remember in our exploration of dilations in the warm-up that we did, we said that the scale factor was the new over the old, which is the image over the pre-image. Okay? Well, the similarity ratio is also the image over the pre-image. The problem is, instead of having the pre-image listed as letters and the image listed as those letters prime, they're giving you a different set of letters. So it's hard to tell which one is the image and which one is the pre-image. However, they give you what's called a similarity statement. And the similarity statement, by the way, this is equal to the similarity ratio, image over pre-image, just like our scale factor. But the similarity statement comes in a strange order. You would expect the pre-image to come first and the image to come second, since the image follows the pre-image. However, in a similarity statement, they actually give you they tell you that the image is similar to its pre-image. That the image is similar to its pre-image. So that's a key thing right there. We all know scale factor, new over old, image over pre-image. That is the same as the similarity ratio. The problem is, when they give you the statement, it's kind of in a strange order. And they don't have A and A prime, so you're looking at it going, well, which one is the image and which one is the pre-image? In this particular one, if they were to tell you that triangle ABC is similar to triangle, well, this is all 60 degrees, 60, 60, 60, 60, 60, 60, since they have to add to 180, divided three ways equally, an equilateral or equiangular triangle, they're all 60 degrees. But if ABC, I'm actually just going to match them in alphabetical order, is congruent, or similar, not congruent, to triangle DEF, then ABC, they're telling us in this similarity statement that ABC is the image, and that DEF is the pre-image. It's kind of a hidden language, and it's a little reverse thinking of what you might expect. So if ABC is the image, then when I'm looking at ratios, the similarity ratio would be any of ABC's lengths because that, after all, is the image, over DEF's lengths. And according to this statement, AB and DE match up. So AB to DE is 3 to 6, which is 1/2. So the similarity ratio, or scale factor, for these triangles is 1/2. Now, similarly, or actually a little bit different, but same idea, if I were to have a statement written that DEF is similar to triangle ABC, then DEF would be the image. The similarity ratio for this, or the scale factor for this, since DEF is the image, the new, it would be DE over AB, which would be 6 over 3, or a ratio of 2 to 1. So it's very important for you to know that when they give you a similarity statement, the first one is the image, and the second is the pre-image. So that when you write your ratio, whether you call it scale factor, U over old, or similarity ratio, you are writing the image over the pre-image to get that ratio. You'll get a very different, or at least a reciprocal answer, depending on which statement is given to you. Determine if the polygons, identifying similar polygons, determine if the polygons are similar. If so, write similarity ratios, or scale factor, and a similarity statement. So there's actually more than one similarity statement we could write. So I'm going to look at this. I'm going to compare. These are supposed to be rectangles, so I'm going to assume, and it's not good to assume, they should have told us, because otherwise this might not be true, that all the angles match up at 90 degrees. And I'm going to check, I mean, if this is a rectangle, then this is also 6, this is also 9, this is also 4, this is also 6. That if I were treating ABCD as a quadrilateral being similar to quadrilateral EFGH, I went around this way, so I went around this way, that 6 and 4's ratio, AB over EF, should be the same as BC over FG. Well, this is 6 over 4, which reduces to 3/2. 9 over 6 also reduces to 3/2. So since the angles, or at least we believe the angles, match up, and the ratios are the same, or the lengths of the sides are proportional, we can say that this quadrilateral is similar to this quadrilateral. It's like a dilation. The only difference is we don't really have a center of dilation for these. But you could think of this being 3/2 the size of this in terms of the lengths. The scale factor to go from here to here was 3/2. When we check the next shape, notice the right angles. So M and N would match up. Notice the single marked angles. So that means that PN, going from the right angle to the small angle, would match up to ML. And again, I'm going to assume that the first is the image. So I would do ML over PN if I'm assuming left to right. It didn't say, so I guess it's okay for us either way to write a similarity statement for this, unless they gave us the ratio. So 60 over 24. Now I'm going to look at the other sides. I should reduce this first, though. 60 over 24, I know 4 goes into both of them. I'm getting 5/2, so that would be 12 goes into both of them, so 5/2. I'm also going to check this small angle to the unmarked angle, so LJ. Small angle to unmarked angle would be PS on the other shape. So that is 75 over 30. 75 to 30 also reduces to 5/2. If it didn't, then at this point I would know that they're not similar. And lastly, the unmarked angle to the right angle is JM. The unmarked angle to the right angle is SN. SN, not SW. So that would be 60, no, not 60, 45 over 18. 9 goes into both of those, which also reduces to 5/2. So at this point, I know that the sides are proportional. All the sides are proportional. I also know that I have one set that's congruent, a second set that's congruent, If I knew that number and did the triangle sum theorem, I would calculate that the third set is also congruent. There's also a reason called third angles theorem, which we did not cover because it's not said for us to cover it till later. But there it is. Apparently we need it already. Sorry about that. At this point, I'm going to let you stop the video because you've already watched the notes for 7.1 in this. I will have a follow-up video for people who miss the in-class portion, which is this, and then you'll be trying these in class as well. Have a great day.